Good morning and welcome to the 21st Annual Exhibit of Hydrogen and Fuel Cell Technologies. There's a broad spectrum of issues we deal with here. Everyone talks about energy efficiency, of course. We know this, we're familiar with how many miles to the gallon in cars. Of course, engineers know that the optimization of uses of energy often depend upon the combined heat and power utilization of that energy. That is not simply a combustion engine that turns something, but something that allows you to use the thermal energy created and the electrical energy in this case. So we'll be talking to a specialist in this field. It's Tobias Thomsen. He is the project manager at Next Energy, and we'll be discussing easy maintenance and design of combined heat and power systems. Please welcome with me Tobias Thomsen.
Thank you. Yeah, thank you for the introduction. So welcome, ladies and gentlemen, to my short presentation about the D2Service project with the title Easy Maintenance and Design of CHP Systems. Shortly, I would like to take the chance to present very shortly Next Energy. So I'm the project manager at Next Energy, and this is our building, and we are a non-profit organization located in Oldenburg. Oldenburg is round about 200 kilometers far away from Hanover, directly next to the ocean, so to the North Sea. And we are founded 2007 by the energy supplier EWE, the federal state of Lower Saxony, and the University of Oldenburg. And we are mainly financed by the public sector as well as the industry. So, Next Energy, some facts. We are divided into 5 divisions. So 3 research divisions. It's the energy storage, photovoltaics, and fuel cells, where I'm located in. And over this is the energy system. They are looking more into the combination of all these research fields. And over this is the modeling and analysis of systems. The fuel cell division is also divided into 4 topics. So up to from the materials up to the CHP system designing. And in the materials, we are looking more in the electrochemistry, for example, in the membranes and the catalysts. In the characterization, we are more in the analytics, so looking into single cells and the degradation, for example. In the mobility, we are looking in fuel cell cars and buses, also fueling stations. And in the CHP system group, where I'm located in, we are looking more in the system integration and the evaluation of CHP system and other energy generating systems. So back to the D2Service project. D2Service starts last year, 1st September 2015, and has a duration of 3 years. The project management agency is the FCHJU, so the Fuel Cell and Hydrogen Joint Undertaken. And the project is coordinated by Next Energy, especially by me. And the participants are Bosal from Belgium, British Gas here from Great Britain, Danterm from Denmark, Energy Partner and Solid Power from Italy, and ZBT as well as Next Energy are from Germany. Yeah, the motivation. What is the motivation of the project? So the durability of subcomponents of CHP system are often very short-lived, or sometimes short-lived. The replacement and the maintenance are very complicated, expensive and time-consuming. So thus the manufacturer have own trained installers or engineers for the maintenance or service aspects. So what do we want to improve? All these points. So the first is the replacement concepts, or the components replacements have to be simplified, and the durability have to be extended so that every component in the system have a very long durability. And the third one, main point, is to develop a manual for craftsmen and installers that allows a cheap and very easy replacement and maintenance of these components. So the scopes of the project are, the first is analysis of the servicing costs, and lessons learned of other projects. For example, Enefield as a European project and Kellogg's as a, for example, German project. And these lessons learned will be used for the design changes required for an easier and more competitive service. In this case, we have Dantherm for the PEM-FC, so for the PEM technology, and Solid Power for the SFC technology. So both manufacturers are working in the first part together to unificate the machines. So in this task, the desulfurization and the water cleanup should be optimized. And in the second part, the some simplifications, for example, the stack and reformer, humidifier, should be optimized by the manufacturer themselves. The next point, I mentioned it before, are the development of the useful manuals for the installers and the craftsmen to reduce the time on machine in service question, for example. And the last points are the validation of the manual as well as of this optimized system in field test. So 12 units should be installed in European, so 6 of each manufacturer, and 1 of each will be installed at Next Energy to evaluate these different CHP units. So now the question, how do we evaluate these CHP units? So therefore we are developing some different test profiles based on, for example, tap water demand, heating, space heating demand, or electrical demand of different building types. So we have like industrial buildings, small enterprises, or residential buildings, family and multifamily houses. Therefore, we are using different guidelines and standards. These are the ERP, so the Eco-Design Directive. Maybe you know from refrigerators, the A+, A++. And the other is the DIN 4709 and VDI 4655. I would like to introduce very shortly these different profiles or these guidelines and standards. So the ERP guideline is a very short test profile of 1 day up to 2 days. And so for us, it's more a performance test. So we have the fluctuations of the demands for tap water in this case. So the Eco-Design Directive is more the tap water profile. And we are looking to what happens with the machine. Have to be shut down when the fluctuation or the demands shrink down, or we have no demand, so have the engine to, or the unit to shut down or to restart or to reduce the energy output. So yeah, as I mentioned, it's more the performance test. The other one is the DIN 4709. It's also a performance test. It's a very short profile of 1 up to 2 days, like the ERP. But here we are not looking into the tap water profiles, it's the heating, the space heating demand. But it's more or less the same as before. The other one is, in this case, the VDI 4655. These are the reference load profiles for single and multifamily houses for use of CHP system or micro CHP systems. In this guideline, we have a categorization of different type days. So we have in total 10 type days. These are categorized in transition, like autumn or spring. Like today, for example, in the summer or in the winter. And also divided into weekday and Sunday, because you have other demands on a Sunday if everybody is at home, for example, or in the weekdays when you are working all the time or have children, for example. And these are also divided into sunny and cloudy. So in total you have 10 type days. If you combine these different type days, which have all a length of around about 24 hours in a high resolution, if you combine these in different seasons, you can generate year profile within a short time. For example, our time-lapse tests for evaluating CHP system have a duration of around about 4 up to 7 weeks. And this allows a very easy way to evaluate systems and characterize different optimization steps in an iterative way, for example. In the next slides, I will show you a short profile in a high resolution. Is in this case a transition weekday sunny. On top you have the electrical demand. It's fluctuating over the whole day. So for example in the nighttime or in the evening you have a higher demand because of let me say television or cooking, for example. And the same is below with the heat demand. So we have the heat demand in yellow and the tap water demand in blue. And here's also the fluctuating. Here you see, for example, in the evening time for a shower or taking a bath, for example. And now is the question, how do we implement these profiles in our systems to analyze CHP systems? So therefore, I will show you this process and instrumentation diagram. We have here on the left side, we have the energy generating components. On the top is the condensing boiler, for example, for peak loads in wintertime, if the CHP unit doesn't have enough thermal or electrical output. Below here, it's a CHP system, or a fuel cell-based CHP system in this case. And there you have the feed-in or the own consumption for electricity. And the thermal output of the unit will be stored in a buffer tank, as you see here in the mid of the picture. And on the right, you have the demands for the thermal demands on top. These are for the tap water profiles. And below, you have the space heating demand. And we are simulating these demands in our test bench. And we are looking how to react these both generating components and evaluate these whole components in an overall system. Therefore, we are measuring on different places, for example, temperature and the flow for every component or subcomponent. And with this, we can calculate the thermal energy and the electrical energy as a gas energy, or the gas consumption will be also measured by flow sensors. And with all these sensors, we can analyze the system regarding annual efficiency, performance, and different kinds of parameters. The next picture shows the real system at Next Energy in a not insulated way. So on the left, you have the solid power, the SFC unit. It's the engine 2500, so 2.5 kilowatt electrical output and 2 kilowatt thermal output. Behind this is the shown buffer tank and the hydraulic system, as well as the flow meters, temperature sensors, and the electrical connections. So, short summary. So at Next Energy, we will evaluate the CHP system under laboratory conditions. So therefore, we can evaluate the annual efficiency with time-lapse tests, also performance and short tests, as well as system efficiency of every subcomponent. With this information, we will give some optimization recommendation to the manufacturers. They will optimize these points, and after this, we will do a repeated evaluation and to review these recommendations. The next point is the manual for an easier and more competitive service and maintenance. This will be the next step in our project. And after this, the proof of concept of the manual as well as of the systems will be done by field tests with 12 units of 6 of Duntherm and 6 of solid power. And the installation site will be in Europe. So thank you, and if you have further questions, feel free to ask now or to come to our booth D57 or get in contact via phone, mail, or our project website. Thank you.
Thank you, Tobias. Do we have a question from the audience? We can go into more detail. Oh, we do.
Well, hi. In the PEM fuel cells, you are talking about ST-PEM or low temperature PEM?
Sorry?
For the PEM fuel cells, you are
Yeah.
talking about low temperature PEM or HT-PEM?
It's low temperature.
And do you think that the thermal energy from the low temperature PEM is enough for heating or something, or whether you'll be designing it oversized for the electrical power requirement?
No, it's mainly the thermal output. We have round about 67 degrees thermal output, and this is more or less enough for space heating or tap water. Because in Germany we will use, or we have to generate temperatures of minimum 60 degrees for tap water. And in this case, it's mainly the thermal output of the PEM fuel cell, and as SOFC, it's more the electrical output, because we have a higher electrical efficiency for the SOFC.
As we can see, the details get more complicated and more interesting. Obviously, when the question of domestic applications arises, the next phase is how do you integrate them into a smart grid so that if I have peak power in my house, my neighbors are actually supplying me. It just doesn't make sense to provide peak power to everyone in the neighborhood if only one person is operating his electric lawnmower while his daughter's using her hair dryer and someone in the basement is drilling a hole and so on. But it's a fascinating topic. Do visit Tobias Thomsen at the booth. It's D57, Next Energy. It's been a pleasure having you here.
Thank you.
Thank you. We'll be back in 1 minute with our next conversation.